But yeah, here we go, 13.3 notes. Grab that and then make sure you're on speaker view so you can see my screen soon. I'm gonna share it right about now and hopefully it looks like this. Yeah, okay, we're good. All right, so I'm gonna run through some things kind of fast. We'll go through other things a little slower as well too, but we'll try to start with a simple daily question from yesterday. I did add comments to your notes from yesterday. They mostly look good, some like small mistakes here and there too. But just to review, if I had a question like this on some kind of assessment, hopefully sooner than later, it says find the pH of a solution. So it's a number that helps us to express the concentration of H plus ions without using crazy scientific notations. This is a hydroxide concentration of 9.2 times 10 to the negative fourth. So there's two ways I could do this guy, but if it's okay with you, I think the first thing I'm gonna do is I'm gonna solve for POH. Is that okay? Yeah. So to solve for POH, and equivalent to the negative log of something that was a concentration of hydroxide ions, and so that's OH minus ions concentration, 9.2 times 10 to the negative fourth. So negative log of 9.2 times 10 to the negative fourth. And then I'll get a POH value then. So I think if I plug that into my calc, negative log of 9.2 times 10 to the negative fourth. You get a number that's like about, and I'm gonna leave this unrounded for right now. I'm gonna say like 3.036 POH. All right. And like another math trick we could do with this guy is, hey, I know that if I have pH and POH of a solution measured together, the total of the pH and POH should be 14. So if I want to solve for the pH, I got on 14 equals pH plus POH. And then my pH will be unsolved for, but I do know my POH is 3.036. And that equals 14. And if I solve for that, I think my answer is going to come out to be that the pH value, whoopsies, I can't do this, pH equals 10.96. Again, it's funky, but my sig figs kind of just tie into my decimals there because that's going to be the values we use at the beginning, and the value in front, the 10 is actually the power of 10 we're talking about in terms of the concentration of hydronium ions there. So there's 10.96 with the correct sig figs too. It's funky. On your work, in terms of what you turned in yesterday, you look pretty good for the sig figs as well too, for the most part. And I think we're good to go. One more thing to mention as well too, I forgot to mention this yesterday, but you don't have units for pH or POH. All right? How are we doing? Does that feel familiar? Feels good? We're okay? All right. Moving along. So this is just things we need to know before we get on to some new-ish things, but really not too crazy for today. So to review, to get 6 equations down from yesterday to manipulate things to get like pH and POHs and common terminology. pH is just found by taking the negative log of the concentration of H plus, or I'll say H3O plus. They're the same thing. Hydronium ions in solution. POH is the exact same thing, but I'm going to do the negative log of the concentration of hydroxide ions in solution. H plus ion concentration, or H3O plus, so you could do that as H3O plus if you wanted to, so either way is fine. Is equivalent to, then to the negative pH, and the concentration of OH minus is then 10 to the negative POH. And lastly, some tricks to go in between the concentrations and pHs and POHs. On the bottom, Kw equals the concentrations of H3O plus or H plus times OH minus. And that is a constant value of 1.0 times 10 to the negative 14. And then lastly, 14 is pH plus POH. There's our review from the other day, okay? All right. So we're gonna talk about like how we can get pH levels when you like consume like lemons, or when you consume like a food that's not quite acidic but has some acidity to it, and how many Tums or like Rolaids you'll need to take to make your tummy feel better as well too. So that comes down to calculating concentrations or pH levels of strong acids first, and then we'll get onto weaker acids and bases after that as well. But down below, this is kind of a newish thing, but I think it makes a lot of sense. We are going to say that these are all going to be strong acids or strong bases that we're using for these questions down below here in these examples. And the key difference between strong acids versus weak acids is that strong acids completely dissociate. So I want to find the pH of the following solutions. I got to find the H plus concentrations of each solution as well in solution. And just to kind of overkill this, if you can write down the reaction for this top one, if I have a concentration of 1.0 times 10 to the negative third molar of HCl, I'm going to write the reaction first down actually when it's in water. So HCl plus H2O liquid. And I think by now you've seen this a ton. Because it's a strong acid, we're going to have an arrow here that shows complete dissociation. It doesn't come back to becoming HCl again. That forms afterwards into Cl minus ions in solution, but also makes H3O plus ions as well. And so what I can see here is that when I have the initial concentration of 1.0 times 10 to the negative third molar of the HCl in the beginning, that makes a 1-to-1 ratio with the H3O plus ion concentration solution. So I want to find the actual pH values. All I got to do is take the actual negative log of the concentration of HCl. And so I'm going to write this down below here. The pH here equals the negative log of the concentration of H3O plus. And if you really wanted to, you could do an ice table and show minus X plus X, but I think we're kind of okay saying that for every one HCl we lose, we'll make one H3O plus. So pH then equals negative log of our 1.0 times 10 to the negative third molar. And I have no idea what that is, but I'll do my calculate fast. I think it's just going to be, is that 3? I think. Negative log, it's 3, right?
Yeah.
Awesome. So that's the power of logs there. pH equals 3. No units, we're good, all right? That's pretty straightforward. Here's going to be how it alters and changes for a strong acid that is not just a 1-to-1 ratio with H3O plus and the initial compound. So if I go over to the right side here, H2SO4 is another strong acid, but the actual reaction looks a little different. So for this reaction, I'm going to do some green. This reaction is similar, but one big difference that I'll set it apart. So I'll have the compound H2SO4, that's aqueous, plus H2O, water, that's going to be a liquid. And again, full dissociation for a strong acid there. And when that happens, the weird part is that H2SO4, because it's a strong acid, both the H's will kind of be stripped off of that guy. And so at the end, we only have SO4, 2 minus. It's kind of crazy. And then we get plus H3O plus ions as well. But I lost 2 H plus ions from H2SO4. And actually, if you look at the reaction right now, it's not balanced. So to balance out the reaction, I need to put a 2 in front of H2O and a 2 in front of H3O plus. So whenever one H2SO4 molecule kind of disperses in the solution, we get 2 hydronium ions formed. So same idea, but a little bit different with the math now to solve from the first thing on the left with HCl.
Wait, Mr. Kim?
Yes, question.
Wait, why wouldn't it just become like H4O instead if you're bringing 2 of the H?
That's a good question. So H4O is actually a super unstable compound that doesn't form a solution. And so instead of making like an H4O mega compound, we just have a lot of water molecules, right? And just 2 of them are going to have to take 1 H plus each for themselves. So that's what happens. So that's a great question, though, actually. I like that. For the work for this guy, it looks almost the same except for one difference here. So again, the pH levels here equals the negative log of my concentrations of H3O plus. And I think we're okay saying this. Since I know that for every one H2SO4, there's 2 hydronium ions formed, when I think about this actual math to solve for the pH, that equals negative log of 2 times the concentration of that compound we had in the beginning. So we're not squaring it, but we are doubling it there. And so if I'll do the exact same math times 2 we have more H plus ions in solution. And so if there's more H plus ions, we get more acidic. And if the more acidic something is, the lower the pH is going to be. And so here I got a pH level that's going to be about, I have 2.7. Oh. And that's my pH levels. Yeah. All right. How I do? Do okay? All right. So that's how I kind of get the pHs of acids. If I want to find the pH of bases, the exact same work. So I'm going to kind of work through these a little faster now, but the only difference with bases is that when you have a strong base, we break apart the base into its components, and that's the only thing in the reaction. So down to the base here for NaOH. In solution, what happens to this guy is that we have NaOH, a base. That's aqueous. And there's going to be an arrow here, and there's actually going to be no other reactant. It doesn't actually add anything to water. It doesn't strip anything off of water as well, too. It just breaks down into Na plus ions and OH ions. This is the weirdo out of the group of 4 here we have. So our strong bases are like decomposition reactions, where the other guys were like single replacement reactions. That's going to be OH minus. And that's also aqueous.
Wait, Mr. Kim, this may be a stupid question, but like, how did you know that that was a strong base?
Right now, I'm just telling you, these are all strong acids or bases. And
Oh, okay.
on like your final exam or like quizzes and stuff, you have a list of strong acids and bases given to you. But you just gotta know like to look. If I say, hey, what's the pH of this thing? First, look up if this is a strong acid or base. So for right now, I'm just telling you it's a strong acid or strong base. But you'll always have a reference list of these are the strong acids, these are the strong bases, and so you should be okay. Okay, so down here, I'll have, I think, the POH being the equal to negative log of the concentration of the hydroxide ions. And so if I do that, I'll get POH equals negative log of 1.0 times 10 to the negative third. So this one actually comes out with a POH being just, again, 3. And lastly, to solve for the pH, that's just going to be 14 minus 3, because again, those two add together, pH and POH equals your 14 value there. So pH is 11. I should say it's 11.00 for sig figs, but there's your value for NaOH. And then the last one on this section is going to be talking about our calcium hydroxide, which is another strong base. And just like we did above, since there's OH2 there, we know that strong bases are going to completely dissociate. So when you write out this reaction here, I'll have calcium hydroxide for this guy. That's going to be aqueous. That completely breaks apart into calcium, 2 plus ions. But now I have 2 hydroxide ions minus aqueous. Okay. So when you solve for this guy again, so POH equals negative log of the concentration of OH minus. And for this case, it's going to be negative log of 2 times the initial concentration of calcium hydroxide. So there's 2 OHs for every 1 calcium hydroxide molecule. Times 10 to the negative third. I think the POH is just like above 2.70, which means that if I do some magic math here, the pH 14 minus that guy, which is why the pH is 11.30. I think I did that mental math correct. So just to kind of review a few things as you're writing that down, if the pH is between 0 or negatives to 7, we're going to say that's acidic. Above 7 is basic. And the true is opposite for POHs. If the POH is less than 7, it's going to be basic. If the POH is greater than 7, it's going to be acidic there. And again, pHs can go below 0 into the negatives and above 14 as well too, based on like how crazy concentrated things can get. All right, questions so far? Doing pretty good on those guys? Not too bad. All right. For the rest of this guy, so in terms of weak acids and bases, here's going to be the big key differences between strong guys and weak guys. It's all on how you write the reaction. So I'm going to write down the generic reaction we had from way before too for weak acids and bases, which was that you have a certain acid, which is in a lot of foods, that's weak, so HA. So there's also an H in front of an acid, that's aqueous. And we'll stick that to some kind of water because we're in a solution. So there's some water there, that's a liquid. Sorry, that's an L. I know it's kind of hard to see. It looks like an E almost, but it's supposed to be an L. In this reaction, because it's a weak acid or a weak base, we don't have the goes to completion arrow. We only have the double harpoons here that shows partial dissociation or equilibrium. And on the other side, we'll get our A minus by himself, so it's kind of lonely there. And also we'll still get hydronium ions, which makes the actual solution acidic. That's aqueous as well too. And one note, if you want to write this down, you can, but when you have a weak acid, even if it's like H2SO4 or H3PO4, if it's a weak acid, no matter what, you'll only lose one H plus ion all the time. You'll never have an equilibrium where you lose 2 or 3 H ions at one time. So it's always going to be a 1 to 1 to 1 to 1 ratio for all of these weak acid, weak base reactions there. Okay, so always be a 1 to 1 reaction there. If I think about ice tables for this dude, what I'm going to do is I'm going to jot down ICE because I think with equilibrium stuff, we need to figure out like concentrations at equilibrium. And if our end goal is to solve for the pH values, we want to figure out how to get the H3O plus ion concentrations. And when we fill these in generically, what we're also going to say is that under HA, we'll have some kind of initial concentration probably given to you in the question. So I would say there is an initial concentration of HA given to us. H2O, dash lines, that's not going to have a concentration at all. And we're not going to have anything for our products there. And then again, the nice part about weak acids and weak bases is that we have all 1 to 1 to 1 ratios. And then the ends, we'll have HA minus X. And then on the other side, X and X. The nice part about these weak acids and bases, though, is that just like before, we are going to have these x's being super small, tiny numbers. And so we'll use the small x rule from what we learned last unit in equilibrium to get rid of that guy. So minus x goes away, and we'll just end up with x's on that right side. So when I think about the Ka expression, what that's going to look like is this, all right? Ka is just the equilibrium expression given an acid. And so the A there just stands for an acid's equilibrium constant. And so I'll have Ka equals, and then for us, I'm going to have on the top the products, H3O plus times A minus, whatever that turns out to be, divided by the initial concentration of HA. And we're not going to do the minus x there because it's just too small. So what's kind of nice is that all the time this turns out to be, and again, like this is going to be showing your work eventually, but write that guy out. And then, so it'll always be K equals x squared on the top divided by the initial concentration of HA on the bottom. All right. I feel like a whale rolling or something like that in the background. But that's how I'll solve for x. And for this case, we talked about solubility before being x, but x, when you solve for it, will actually be the concentration of H3O plus. And if you have the concentration of H3O plus, you can do whatever you need to do for the rest of this guy then, okay? All right. Same thing applies for our base. And so I'm gonna go down and do kind of the generic results for our base then as well, okay? So for a weak base generic reaction, I'm gonna go back and kind of write things down in the same color scheme here. The base will look a little bit different. So I'll have a base, so B, that's gonna be an aqueous solution, plus H2O liquid. And at most, that base will only take off one H plus ion. Will never take off more than one in solution ever. So it'll become BH plus ions in solution plus OH minus ions. And so again, the nice part about weak acids and weak bases are that you always have a 1 to 1 to 1 to 1 ratio. So again, here, if I think about my ice table, so if I ice this guy up, ice, exact same form. So there's that. And then I'm gonna have like the same number filter equal to. I'll have like the initial concentration of a base minus X. This is the base minus X here. Nothing, nothing, nothing for water. Here for products. Plus X there. And lastly, X is so small, it goes away on the reactant side. All right. So for KB expressions, the equilibrium expressions for bases, what you'll have is very similar to above. KB equals the concentrations of whatever your products are afterwards, OH minus, divided by concentration of B beginning, which is going to turn out to be, again, for us, X squared over BO. And then in this case, the difference is that X equals the concentration of OH minus. Question.
What does O mean? I'm really.
The O right here, like where B is and stuff, is that what you're asking for, correct?
Yeah.
That just means like the initial starting amount of whatever we give you. So the initial concentration of the base, or above is the initial concentration of the acid for the HA0 thing there, okay? So 0 just means initial concentrations. All right, let's do one practice question together, and then I'm going to be done and out of your way soon here, okay? So for the one practice question down below, examples, we're gonna start with propanoic acid, which is this crazy HC3H5O2 compound there, has a Ka of 1.3, okay? We gotta find all these things from H3O plus and POH of a 0.100 solution. So what we're gonna do first is we're gonna solve for the actual X in this question by writing on the reaction. So I'm gonna jot down the reaction here. HC3H5O2 aqueous plus H2O to liquid. And this is going to be a weak acid, and so I'm going to say this is in equilibrium with. That first compound will lose its H and still become just C3H5O2 minus charge, because when you lose an H plus ion, that plus goes away with it. So if we lose a plus charge, it's going to be a negative charge afterwards. Plus H3O plus aqueous. And so let's make an ice table for this guy now once we have that reaction down. And so I'll do ICE. Everything's in a 1-to-1 ratio, which makes our life super nice. And when I have that done, I'm going to have the initial concentration for HC3H5O2, and that was given to us. That was 0.100 molar. And so I'll put that down for the initial concentration of HC3H5O2 for our acid there. And then I'll have nothing for the H2Os, zeros for the products. And then now, because again, it's a 1-to-1 ratio, I'll do minus X for the reactant plus X for the products there. So I'll get 0.100 minus X, X and X. We can solve for stuff now, so let's do it. For our actual K values to solve for here, I'll write this down below here, okay? Ka for this equals the concentrations of C3H5O2 minus times H3O plus divided by that HC3H5O2 compound. So when I do that, I will get that your Ka value, which equals, I think in the question, 1.3 times 10 to the negative fifth. That's right up there. I'm gonna do some purple now. So I'll do 1.3 times 10 to the negative fifth equals, on the top, the equilibrium concentrations of those two products is just X and X, or just X squared, divided by the initial concentration of that acid in the beginning, which was 0.100. And I can solve for X. So if you want to take like a little bit of time to solve for X there, I have no idea what it's going to be. So 1.3 times, let's just cause 10, right? Times 0.1 and the square root of that answer. If you solve for x and not x squared, I got this number, okay? So look up and see what you got your number, but I got this value that's unrounded. Does that look similar? Yeah? Maybe, possibly.
Yeah.
Yeah, that's what I got.
So that's my x value, which is then also equal to my concentration of H3O plus. So I have here the concentration of H3O plus is equal to 0.00, let's go with 2 sig figs, 11 molar, okay? You could do a ton of things now to solve for these other three guys here. So I'm gonna do this where I find the pH next. So I'm gonna take the negative log of that answer, the pH, just to get my math rolling for the other stuff. So pH equals negative log of that. So negative log of 0.00114001, oh my bad, 02. And so that means that my pH then, I got a number of like 2.94 with 2 sig figs there, okay? To find POH, POH is just going to be 14 minus that 2.94. So POH equals 14 minus 2.94. I can't do much math. 11.06. And then lastly, solve for the concentration of OH minus ions. It's going to equal to, I think, the 10 to the negative 11.06 power. And so if I solve for that 10 to the negative 11.06, I get a crazy funky number that looks like this for OH minus concentrations. It looks like 8.71 times 10 to the, oh, that's 3 sig figs, 7 times 10 to the negative 12th molar, okay? All right, I said a ton of stuff really fast, but hopefully you got most of that stuff down. This is gonna be like the hardest thing we do for acids and bases. Tomorrow I'm gonna start off just reviewing with one of these guys here. And then Thursday is just gonna be a review, and then Friday is kind of a unit review for what we did, and then spring break's gonna hit us there, okay? Your homework's gonna be to try to check number 2 and get that guy going. The difference between number 1 and number 2 on these practice questions are gonna be, one deals with acids and H3O plus ion concentrations. Number 2, when you solve for X for number 2, because we're giving you a base, X will be your OH minus concentration. So kind of go backwards what we just did there. So when you do number 2, make sure you are knowing that X, when you solve for it, equals the OH minus concentration there. And that should be it, okay? Questions for me on this guy here? Are we feeling okay on what we just saw? Or?
All good.
We're good? Nice, okay. Yeah, that's all I have for right now. You guys were awesome. That was